We're talking about stationary points. And it says intervals of increasing and decreasing, but it's not meant to say that. That's all right. Must have been a typo. All right. So if we have f dash of x, and if we substitute a number into that, what do we get?
F dash of the number.
F dash of the number, which gives us what in terms of the graph? It gives us the...
Y coordinate.
Gives us the slope.
That one.
Yep. It gives us the slope of the graph of y equals f of x. Do we agree? Yeah, apparently we do. I'm recording this at the same time, so of the graph of y equals f of x. All right? Now, if that slope is positive, what does that mean about the graph? It's going upward. The graph is increasing. Okay, very good. The graph is increasing. Okay, and so it'll probably look something like this, or like that, or like that. Any of those, the graph is actually increasing, and so the slope is positive. What about when the slope is 0? Very good. The graph is actually, at that moment, horizontal. All right? So the graph is horizontal. And what we say that has a special name, whenever the graph is horizontal, we call that a stationary point. All right? So that's, this new section is going to be all about stationary points. What about if the graph is negative?
It'll be
Because f dash of x is negative, sorry.
opposite of what we did plus.
Very good, it'll be the opposite of the plus. So instead of increasing, it will be decreasing. So the graph is decreasing.
I was focusing on what I said.
If the slope is negative, the graph is decreasing. All right. And so if you think about how that would look as an actual graph, it would look like that, or like that. Yeah? That's quite pretty, isn't it, actually? So then if we think about zeros of functions, at a 0 of just a plain old function, we're not talking about the derivative at the moment. At a 0 of a function, the function cuts or touches the x-axis. Do we agree with that?
Yeah.
Great, someone does. So at a 0, the function cuts or touches the x-axis. I think I'm going to sit and write this because it's... All right. But if we talk about a turning point, what happens to a function at a turning point? If you think about a turning point, so something like that looks like that, what happens to the function in words? Very good, Letitia. It goes from increasing to decreasing. Excellent. Have you looked at the answers? No, you can't have. So the function changes from being increasing slope, to being a decreasing slope, or vice versa. It can go from being decreasing to increasing if it looked like that. Okay? At a stationary point, and this is all a little bit technical at the start, but anyway, at a stationary point, the function, as we said above, is momentarily horizontal, or it has a horizontal tangent. Now, they're not necessarily the same thing. Okay, so the function is horizontal or has a horizontal tangent. And this is also true for turning points. So why we're specifying that is that all stationary points are horizontal and all turning points are stationary points because of that. So this is a turning point and that's a stationary point as well. But not all stationary points are necessarily turning points. Okay, so I'll show you some examples of that. But if you just write that in, all turning points are stationary points, but not all stationary points are turning points. This is an example of something that has a horizontal part to it, but it's not a turning point because it doesn't actually change from increasing to decreasing or decreasing to increasing. It goes from increasing to increasing. It goes from concave down to concave up. All right, that's the definition of a point of inflection, remember. So that's why we specify that bit there. All right, a graph is said to be stationary when it's momentarily horizontal. Momentarily horizontal. It's neither increasing or decreasing. Okay, so at that point in time, it's like it's stopped moving. If you were talking about, say, a roller coaster, when you're actually at the top of a roller coaster, you'd probably talk about this in physics, you're not actually moving. At that point, when you change direction from going from increasing your up to decreasing down, you actually stop. It doesn't seem like you do, but you do, momentarily. So there is a horizontal tangent. And so, to solve for stationary points, what do you reckon we need to find? We need to find the point when what? Very good, Costa. The slope is equal to 0. And how do you find out when the slope is equal to 0? What do you do? What equals 0 if the slope equals 0? M. And in terms of derivatives, what equals 0 when the slope is 0? F dash of x equals 0. Good. We solve for f dash of x equal to 0, and that's the same as dy on dx equals 0, isn't it? All right? They mean the same thing. They are the same thing. F dash of x equals 0 and dy on dx equals 0. So there are 4 cases of possible signs. It's a bit small, isn't it? There's 4 cases of possible signs on either side of a critical value on the sign diagram of f dash of x. You have no idea what that means, do you? All right, write it. There are 4 cases. The critical value is simply when if you do f dash of x equals 0 and you get the answer for x for that, that's called a critical value. All right, that's all that means. So there's 4 cases of possible signs on either side of a critical value on the sign diagram of f dash of x. I'm going to draw you 4 side diagrams and you'll see what we mean. So if we go find when f dash of x equals 0 and you got that x equaled a, for example, where a just represents a number. I'm going to draw a sign diagram, and when you draw a sign diagram, you put on the bottom of the sign diagram the values when your function is equal to 0. So I'm just going to put a on each of these sign diagrams. Okay? These are sign diagrams of f dash of x. They're telling you when the function is equal to 0 and the behaviour of the function on either side of that 0. Okay? Sign diagram. Yeah? Remember them from last year? All right. If it's positive over here and negative over here, all right, so if your function is positive over on slope on one side and negative on the other, the shape of it will look like that. Okay? Because it's a positive slope to a negative slope. If it's a negative slope to a positive slope, it's going to look like that. That's a negative slope, that's a positive slope. If it's a positive slope to a positive slope, which means that it's always increasing, it's going to look like that. And if it's a negative slope to a negative slope, which means it's always decreasing, it's going to look like that. Okay? Good. All right, they're the 4 cases. So the top one's called a local maximum. The next one's called a local minimum. So that's a local max, that's a local min. And then the next 2 are called stationary points of inflection. So you might not have, in your investigation, you were meant to find out that there are 2 types of points of inflection, and stationary points of inflection are one of them, where they actually go horizontal. Now these are all stationary points. Okay, but they're not all turning points. Yeah? Cool. So then if we go and do an example where we have to find and classify the stationary points of the following functions. How do you reckon you're going to do that if you want to find the stationary point? We're going to do dy on dx equals, now we're going to use the power rule, so we're going to multiply down and subtract 1. 3x squared, multiply down, take 6x, subtract 1, multiply down, we've got 9x, so that's really 9x to the 1, so we multiply down, we're just going to get 1. So that's just going to be take 9, and then of course the derivative of 5 is always 0. Alright, so we found the derivative. Then to be able to find the stationary points, all we've got to do is find when the derivative is equal to 0. dy on dx equals 0 when 3x squared take 6x take 9 is equal to 0. Now if I've got that, alright, what am I going to do first off to solve that? Very good. You're going to take out a common factor, aren't you? So you're going to put 3 outside the front and you're going to get x squared take 2x take 3 is equal to 0. Then you're going to do sum and product. Your product is negative 3. Your product is negative 3, so what are factors of negative 3?
1 and 2.
1 and...
I mean 3 and 1.
Negative 3, factors of negative 3?
Negative 3.
Negative 3 and 1, okay, negative 3 and 1. Does negative 3 plus 1 make negative 2?
Yeah.
Yeah, cool. So we've got our factors, all right? So you don't even have to show that working out anymore, but you can if it helps you. So you'd go 3 outside of x take 3 times x plus 1 equals 0. Does everyone understand how that came to be? Sorry? You good?
Negative 3 plus x plus 8.
Cool. All right, and then using now factor law, then x take 3 equals 0 or x plus 1 equals 0. So x is going to equal 3 or negative 1. All right, so they are telling you what? What are they actually telling you, those values?
Where the x equals 0.
Where x equals 0,
Slope equals 0.
where the slope equals 0. Good, okay. So they're telling you where the slope is equals 0. They're telling you this something point. Stationary points, okay? They're telling you the stationary points. You don't know yet if it's a stationary point of inflection, okay? But think about it. Could it be a stationary point of inflection? It's a cubic, so could it have stationary points of inflection? Yeah, it could. Might not necessarily, but it could. Okay, so we need to check that. So then we do a sign diagram of f dash of x. All right? Let's do a sign diagram of f dash of x. Remember, when you do a sign diagram, you plot the points where the function is 0. So we're going to put negative 1 and 3. Okay? Now, whenever you've got a sign diagram, all you have to do is put a number that's less than negative 1, greater than negative 1, into your f dash of x and work out what value it is, whether it's positive or negative. This doesn't have to be done exactly at all. But if we just think about that, just the really important thing to remember is that we're talking about the sign diagram of f dash of x, not the sign diagram of f of x here. Okay? We're trying to work out when the slope function is positive and negative. Yeah? So you're always going to do the sign diagram of f dash of x, not of the actual function. So let's try when x is equal to 0 is 3x squared take 6x take 9. What's that going to be? Positive or negative?
Negative.
It's going to be negative. Very good. All right. Then if we pick negative 2, we'd get 3 bracket negative 2 squared take 6 by negative 2 take 9. So that's going to be positive, isn't it? Yeah, because negative 2 squared is 4. And that's going to be positive. So they're going to have 2 big positive numbers and then 1 negative number. So that's just going to be positive. Do we agree? because this bit's going to be positive, this bit is going to be positive. They're two relatively big numbers and you're only taking away 9, so it's going to be positive. And then over here, if we just pick a number bigger than 3, say 5. So again, you get 3 by 5 squared, take 6 by 5, take 9. Now we might want to check that. 5 squared is what, 25? So 3 by 5 is 75. Yep. We're going to get 75, take 30, take 9. So even though we've got a bit of a bigger number, it's still going to be positive. All right? So that's saying what? What is that actually saying? Shogi. What's it saying? Costa, you go. You were right.
It goes up and down.
Okay, it goes up and down. Yep. Could you tell me approximately where? So what's the shape between the positive and the negative?
It comes from the top. And when it hits -1, it goes beneath the x-axis.
Goes beneath the x-axis. Is it talking about, that would be if it was talking about the sign diagram of f of x. But because we're talking about the sign diagram of f dash of x, remember we're talking about slope. So Shogi, what do you reckon? Talk. No? Mark? Yeah, okay, good. It goes up, then down, then up. All right, very good. It's going to go up. Watch this. It's going to go increasing to decreasing. Positive slope to negative slope there. Over here, it's going to go from negative slope to positive slope. All right? So that is actually telling you an approximate picture of what this function could look like. It's going to go positive, negative, positive. Yeah? Is that all a little bit confusing, or do we understand that? It's okay? Yeah. Sorry? In this section, when you get questions, like this question up here, what you've got to really make sure you do is write down all your information really clearly, because they're not actually that difficult, but they could throw you. So, we get told, Alex, can you read that out for me?
Curve of the equation y equals x to the power of 3 plus ax squared plus bx plus c passes through 0, 5 and has a stationary point at 2, 7, 1, a, b, and c.
Very good, thanks. So can anyone tell me a bit of information that you know from that?
It passes through point 0.5 and has a stationary point 2.7.
Good job, Costa. It does. And that's actually telling you 3 bits of information. The fact that it says it passes through 0.5, that's a beautiful 5. That's a 5. It passes. Okay. Passes through 0.5. All right. That's the value of a point on f of x. So that is telling you that f of 0 equals 5. Do we agree? Yeah. I'm going to change this to talking about f of x because I like it better than y. So you might want to scribble out the y. All right. So that's one bit of information. Then you've got another bit about 2, 7. Now it says it has a stationary point there. So that is actually telling you 2 bits of information. Can anyone tell me what one bit of information would be?
When the slope equals 0.
It's when the slope is equal to 0. Very good. So that in terms of function notation, what does that actually mean? Slope equals 0 means?
dy on dx is 0.
Yep, d1 dx at x equals 2 equals 0. In terms of f of x, how would you say it?
Equals 7.
F dash of... f dash of 2 would equal 0. Do we agree with that?
Yeah.
And we also know, because we've been told it's a point, it's a stationary point, which means it does lie on the line, so that f of 2 equals 7. Not f dash of 2, but f of 2 equals 7, because we know that it's a point that lies on the curve. So you've got 3 pieces of information there, which is wonderful because you've got 3 variables. So you're just going to use all the different pieces of information. We know that f of x equals x cubed plus ax squared plus bx plus c. Yep. That's just from the question. So you can't disagree with that. So when you're solving them, just use the bits of information systematically. And it would be really good if you wrote out the bits of information like I've done there, because that's just going to make it way simpler for you. So you're going to go 1. Now f of 0 equals 5. All right, that's what we said. If f of 0 equals 5, what can you say about the value of c?
C is 5.
C is 5, okay? C is 5 because when we substitute in 0 for x, we're going to get rid of that, and that, and that, and we're just going to get left with c. So c must be equal to 5. Brilliant, we've already found one variable. Now the next bit, we know that f of 2 equals 7. I'm just going to work with f of x before I work with f dash of x. So let's substitute that in. That's going to give me 2 cubed plus a times 2 squared, so that's going to be 4a, plus 2 times b times 2, so 2b, plus 5, because I now know that c equals 5, equals what?
7.
It equals 7. Cool. All right. Now if we simplify that and collect our like terms together, 2 cubed is just 8. So that's going to give us 4a plus 2b plus 13 equals 7, or 4a plus 2b equals negative 6. Cool. We've got an equation. Brilliant. So we've used f of 0 equals 5. We've used f of 2 equals 7. So what's a little bit of information left that we have to use? What's the one bit of information we haven't used yet? We haven't used yet that f dash of 2 is equal to 0. So let's use that. F dash of 2 equals 0. So to use that, we have to find what function? Kai. What function do we have to find in order to be able to use the information that f dash of 2 is equal to 0?
I have no idea.
That's okay. You haven't been here. Ashley.
Wait, what was the question?
So to be able to use the piece of information that f dash of 2 equals 0, what function do you need? To use this, I have to find f dash of x, so let's find it. F dash of x is going to equal, let's differentiate that top bit. Who's brave enough with the power rule to have a go at differentiating that? Can you do that on your own? What we're going to get is f dash of x equals 3x squared plus 2ax plus b.
What
Okay.
happens to the C?
What happens to the c? The derivative of a constant is
Oh, yeah.
is always 0?
Always
Yeah.
0.
Good question though. Derivative of a constant is always 0. So now we've got f dash of x. Now we can use that piece of information. So, huh?
Why don't you keep bx?
Why don't I keep bx? Because I'm taking the derivative of b of x. Remember, b of x is really bx to the 1. If I multiply down, I'm going to get b times 1 x. Then I do take 1. Multiply down, subtract 1. So 1 take 1 is 0, and x to the 0 is going to be 1. Yeah? Good question.
B times 1 times.
All right, so it's just going to be b times 1, which is just b. All right, so let's do f dash of 2 now. And I'm just not going to write that because I'm going to say what it's equal to. So I'm going to go 3, and then let's substitute in 2. 3 times 2 squared plus 2a times 2 plus b is going to equal what? It's going to equal 0. Cool. All right, we simplified that. You get 12 plus 4a plus b equals 0. So you get 4a plus b equals negative 12. All right. Now, what do we have? We have twin equations. Is that what you said, Ella? 2 equations. We have simultaneous equations. Equations 1 and 2. So we're just going to solve them, and I'm going to solve them using elimination. The reason I'm doing elimination is I've got 4a in both of them, so I can just eliminate them from each other. All right, remember there's 2 methods of solving using simultaneous equations. So up we go. Let's go. So I am going to do step 4, and it's really, see how I've laid out my steps really logically? Okay, so that's really helps your brain if you can write your information in consistent steps, because you'll know what process you're doing when you're doing a question like this, and you won't get lost in what you've done and what you haven't done. So I'm just going to write myself this note. I'm going to subtract equation 2 from equation 1. All right, so I get 4a plus 2b equals negative 6. Under here, 4a plus b equals negative 12. If I subtract those equations from each other, the 4a's are going to cancel out. 2b take b is just going to be equal to b. And negative 6 take negative 12 is going to be equal to what? Negative 6 take negative 12. Not negative 18. Because negative 6 take negative 12. It's just going to equal 6, isn't it? Okay, so I'm just going to get B equals 6. Brilliant. And then I'm going to, step 5, substitute that, which is I'm going to call 3, into 1. So I'm going to substitute 3 into 1 in order to find A. So I get 4A plus 6 equals negative 12. Oops. Okay, and so 4A equals negative 18. A equals negative 18 on 4, which is the same as negative 9 over 2. Woo! We've done it. So, sorry? Sorry, what was the question?
The one you've labelled as 1 is 4A plus 2B.
I think you subtracted 1 from 2.
Did I subtract 1 from 2? I subtracted 2 from 1.
I don't think it matters because you're solving for.
Because I did 4A plus 2B equals negative 6. That's 1. And from that, I subtracted 4A plus B equals negative 12. Yeah? Where did the 6 come from? So the 6 came from, I subtracted the two equations and I got 4A and 4A. They cancelled out each other. 2B take B is B. And then negative 6 take negative 12 is 6. Yeah. Another question?
Equation 1, 2B. Yeah, that's what I was saying. What you've listed as equation 1 is 4A plus 2B.
Like 4A plus
Yeah. Yeah. 4A plus 2B equals negative 6.
So then sub 3 into 1 would be 4A plus 6.
2 lots of 6.
Okay, yeah. I get what you're saying. So I subbed 3 into 2, didn't I? Is that what I did?
Yes, you said
Yeah.
3.
Brilliant. Thank you. All right. So finally, just write out what values. You'd write that A equals negative 9 on 2, B equals 6, and C equals 5. Another question. Yeah.
When you did 4A plus 6 equals negative 12, should that be 4A plus 12 equals negative 12? No,
Well, I actually substituted it into equation 2, and equation 2 is 4A plus B equals negative 12. Equation 2, yeah. Okay. Cool. All right. Next page. Is this making sense? Do you have questions? It's making sense? You sure? It is? Yeah. It's okay? All right. Next. If we're considering a curve over a restricted domain, and by that we mean that it's not a graph that goes on forever and ever. It's a graph that actually stops at specific points. It's got endpoints. So we'd say that A is less than or equal to X, which is less than or equal to B, because you all know by now that the domain is the X values, not the Y values, yes? Yes. All right, the range is the Y values. Or over the interval A, or over the interval AB, yeah? Okay. So if we're doing this case, we're talking about, this is a global minimum, this is a global maximum. All right, what that means is over that whole curve, that is the smallest point on the curve, the global minimum, and that is the biggest point on the curve, the global maximum. So that's the global minimum, and that's the global maximum. Okay. These ones in between are just called local, because they're not the overall biggest number or smallest number, but they are minimum and maximum in your function. So that's called a local minimum, and that is called a local maximum. All right, now the next one's very similar, apart from you'll notice that this point is actually what? What is this point? In terms of it's a global minimum, all right? So it's both a local and a global minimum. And in this case, the endpoint is not actually a global minimum, so it's not always going to be. That one's a local max, and that one over here is a global max. All right? So if you're being asked to find the greatest and least values of the function, or you're being asked to find the global minimums and maximums, what you have to make sure you do is that you consider both the turning points and the endpoints, because sometimes the endpoints will be global. So in order to find the global maximum and minimum, both the turning points and the endpoints must be considered. With this, you're being asked to find the greatest and least value of the function on this interval. What do you think you're going to find? You're going to find the...
Global max and global min.
You're going to find the global max and global min. Very good. That's what it's actually asking for, the global max and min. And to do that, what are you going to find? You're going to find the turning points of the function. How do you find the turning points of the function? You find when the slope is equal to 0. Very good. You find when dy and dx is equal to 0. You find where f dash of x is equal to 0. All means the same thing. So let's first, in order to do that, find f dash of x. What's f dash of x going to equal? It's going to equal 0, but before we know it's equal to 0, let's just calculate it. Let's find the derivative of that function. Go. So let's find the derivative. Someone be brave. Tell me, what is it?
3x squared plus 12x.
It's 3x squared, take 12x, isn't it?
Yeah,
Yep.
sorry,
Cool. No, that's all good. Now, I'm actually going to factorize that. But actually, I won't factorize it yet. I'm going to find when f dash of x equals 0, that means that 3x squared take 12x equals 0. Correct? So let's factorize. That's going to give me 3x bracket what? If I factorize that, anyone? X minus 4. Very good. Equals 0. So what does x equal?
4.
X equals 4 or 4 or 0. Very good, because 3x could equal 0, couldn't it? And if 3x equals 0, x is also equal to 0. So we found the derivative. We've equated the derivative to 0. So what are we going to do next? We're going to find the sign diagram. The sign diagram. Yes. You'll be doing lots of sign diagrams. Sign diagram of what? F of x or f dash of x? F dash of x, okay? Always pretty much. In this case, you're going to be doing sign diagrams of f dash of x. So let's go 0 to 4. Now, can you get a stationary point of inflection? Can you? No, you can't get a stationary point of inflection. Why can't you get a stationary point of inflection? Yeah, because I said so.
You can't go up when you slope 0.
No.
Because it doesn't go up and down enough times.
Yes. Why doesn't it go up and down enough times?
Because it's not a quadratic.
It's
not
it's not a cubic.
a cubic.
Very good. Excellent. Notice that your derivative is a quadratic. Can quadratics ever have stationary points of inflection? Nope. They only have turning points. All right? So you know, that means that's really good, because that means all you have to do is find the value in the middle, and then you know that the values on either side are just going to be opposite. Okay? So let's pick a value in the middle. Say let's pick 1. So 3 take 12. I'm just picking 1 and putting it into f dash of x. 3 take 12 is a negative. And because I know that I can't have stationary points of inflection, that must mean I have a turning point at those critical points. And so I just know that that slope's going to change sign.
Wait, so does this only apply when you got that 0?
That only applies, the reason I can do that is because I know that the derivative is a quadratic. And that quadratics only have turning points. So I know that the slope has to change at the turning point.
So,
If it was a cubic, it could be like that.
mm-hmm.
And therefore I could have a turning point, but I could go from positive to positive. I don't have to go from positive to negative. But if I know that it's a turning point, I have to go from positive to negative or from negative to positive.
Wait, so on the sign diagram, is it says
So the sign diagram, what
so
I...
you knew that because you had a 0 there, or
Okay, I knew that this one was negative because I substituted in 1 into this equation.
how did you know that you only need, like, how did you know that you only need to find the middle one and the other two were going to be the opposite? Like, how did you know that?
Because I knew that at the turning points, it's going to change sign because it's a turning point. It's not a stationary point of inflection.
Okay, and
You sure?
where does it say that it's the turning?
It doesn't. It doesn't say it's a turning point. But people, the teacher's asking a very good question over here. All right, so it doesn't say it's a turning point, but I know it's a quadratic. And I know quadratics only have turning points and they don't have stationary points of inflection.
Right. Okay. So you know it's a quadratic.
Function.
Okay. Because of this square.
And yeah, because of
Yeah.
the squared.
Okay.
Yeah?
Okay.
Cool. Why do we have phones out, people?
Measuring my heart rate.
Why are you measuring your heart rate? Are you stressed? All right, we're going to stop. I'm going to stop talking in a sec. All right, so we've got, we know the sign diagram. So we know potential local minimum and local maximum. What I'm just going to write down here, though, is remember I have to check the endpoints as well. People, critical values and the y coordinates. By critical values, I mean all the values that could possibly be, all the x values that could possibly be global maximum or minimum. All right? And they are the endpoints and they're also the turning points. So we were told that it goes from -5 on 2 to x to 5. So I know one of the values could be -5 on 2. Then I know I've got my values where it actually equals 0, which we found. And then I know the other endpoint is 5. So they're all the x values that I could possibly have. Now, the y values, and you're just going to have to trust me on this, you would actually have to calculate this. And a really easy way to calculate this would be to draw the derivative on your Casio calculator, to actually draw the derivative and then just put in and find the y calc so that you don't actually have to calculate it. And so the y coordinates are these. All right. So we therefore can see that the greatest value of the function is here. No, that's the least value. The greatest value is 5. Where the numbers come from. So they are the y values that correspond with the critical values, and the critical values are the turning points or the endpoints. So I was told that the graph went from -5 on 2 to 5 up there. So they're the endpoints. All right. And then 0 and 4 are my turning points. And then I just found the y values and I just put them in without actually going and finding them.
Use a calculator to
Yeah,
find
you
it.
just
Okay.
use the calculator to find them. All right. So our answer to our question is which is the greatest and least value of the function. The greatest value, remember it's always important to actually answer the question and not just do the working out. The greatest value of f of x is 5, and the least value is -48 and an eighth. And I don't have to write a coordinate because it's actually asking me for a value of f of x, and the y coordinate is f of x, so that's cool. So we're done. 20 is greater than 5, but the...
It's out of the domain.
no, it's not. It's -20. Well done, Mark. Good pick up. All right. And so we're done. Cool? Happy?